Let's continue with measures of variability. Now I want to introduce two statistics for standardized measurements. The first one is called coefficient of variation. So it's say, right? Coefficient of variation is addressed by this letter say, lowercase say. It is the ratio between standard deviation and the mean value of your data set, which is addressed by X bar. Why is it called standardized? Because the standard deviation here is divided by X bar, or we can say is normalized or is standardized by its own mean value. After this standardization, you can compare say values from different data sets. They are comparable now because each of them has been standardized by its own mean value. I mean, by each group's mean value, each data set's mean value. So it's relative variability and the mean standardized standard deviation. So we use the data set's mean to standardize standard deviation. Okay, sounds tricky, but it's just a simple standardization, normalization process. And we have another standardized measure for variability. It's widely used and it's called Z-score. Okay, here, since data are distributed with different means and different degrees of variability in different data sets, okay, it is common to standardize observations. So again, what's the purpose of normalization? What's the purpose of standardization here? The purpose is to make different data sets comparable with each other. Okay, so here, a Z-score for a specific observation, I, is a ratio between numerator and denominator. Denominator is this data set's standard deviation. Standard deviation here is used to standardize the distance between that observation and the mean observation, or you can say the mean of observations, right? So xi is a specific observation, x bar is a mean value of all observations in this data set, right? So you calculate the difference between them and standardize that distance by the standard deviation of this data group, of this data set. So you can see here, Z-score is specific for each observation, which means that for each I value or for each specific observation, you can calculate a Z-score for it, for that observation. Okay, then let's talk about the shape or relative position of histograms for data sets. We're using this word, is called skewness. So skewness is the measures the degree of asymmetry, okay, shown by a histogram, right, exhibited by the data. For any data set, you can always draw a histogram for it. The horizontal axis is the specific value of your observations in this data set. The vertical axis is the frequency of each possible value for your observation, right? It's very straightforward, right? So extent to which values are evenly or unevenly distributed about the mean. So here, the baseline is still the mean. So the formula is here. Okay, so you again, you calculate the distance between a specific observation and the mean of the data set, and you calculate the result to the power of 3, right? And you sum you do this for all observations in your data set and divide that value by n, which is the number of the observations, and then divide that by s to the power of 3. S is the standard deviation. Okay, so eventually symmetric data distribution has a zero skewness. Skewed data distribution has a positive or negative skewness. Here are some very typical examples. So horizontal axis is for data value, or vertical axis is for frequency. So in this two-dimensional Cartesian coordinate system, we're actually drawing histograms for 3 data sets, and we have 3 curves here. They are used to address the shape of 3 data sets. So for data set 1, let's just assume data set 1, its skewness is 0, which means that there is no skewness for this data set. So you can say that this black curve is what? Is symmetric, right? It's symmetric. If the skewness of data set 2 is larger than 0, then you can say this blue curve is used to address the shape of the histogram of data set 2. And it is skewed. It's larger than 0, means that on the right side, the histogram has a long tail. So skewness larger than 0, the peak of the histogram is going to the left, and on the right side, there is a long tail. On the other hand, for data set 3, its skewness is smaller than 0, in other words, negative. Then we have this red curve to address the shape of the histogram of data set 3. You can see that the peak of the histogram is to the right side, and it has a long tail to the left side of the histogram. So next time when you are checking a specific value for skewness, if it is 0, in your mind, this black curve should appear. If it is larger than 0, then you should expect a histogram with a shape of this blue curve. If the skewness you're looking at is smaller than 0, you should expect that the histogram of the data set associated with this negative skewness should be like this blue curve, red curve, okay? The peak is to the right, and there is a long tail to the left side. This is skewness, so it is used to address the asymmetry of your data set. Of course, if it is 0, it's symmetric, right? Okay, kurtosis. Kurtosis is another statistic to address the flatness or peakedness of a data set. Again, it is related to the histogram. If you compare the formula of kurtosis to skewness, the only difference is that here we do not calculate the power to the third. Instead of that, we calculate the distance between each observation and mean value to the power of 4 instead of 3. Similarly, for standard deviation, it's still to the power of 4 instead of 3. If you change this to 3, change this to 3, change these 2 powers to 3, then you're talking about skewness, right? So for kurtosis, if kurtosis is equal to 3, then you have a normal distribution or standard distribution. If kurtosis is larger than 3, you have something called leptotic, right? High degree of peakedness. If kurtosis is smaller than 3, you have something called platykurtic, relatively flat histogram. Okay, let me show you. If your kurtosis value is equal to 3, you have this black curve, right? Not too flat, not too peaked. But if your kurtosis value is smaller than 3, then you have this blue curve to address the histogram of your data set. Compared to the black curve, it is fatter, it is flatter, right? It's flatter. But if your kurtosis value of your data set is larger than 3, then you have this thinner, higher, less flattened red curve to address the shape of the histogram of your data set. So kurtosis here is not to address asymmetry or symmetry. It is here to address the flatness of the histogram of your data set. Okay, so now let's add spatial context to some measures we have discussed in this lecture. Measures of spatial central tendency. We talked about mean. We talked about weighted, not weighted mean. We're going to talk about weighted mean center here. We talked about median, but there was no spatial context, which means the location of those data sets, locations of all those observations did not matter, but now they matter, because for now we're talking about statistics with spatial context, which means that the location of each observation matters. Okay, so we're going to talk about mean center. When we're talking about center, it has the context of space. Okay, center, geographic center. Okay, weighted mean center, median center, weighted median center, and we're also going to introduce measures of spatial variability, standard distance and relative distance. Okay, so these are what we're going to talk about for the rest of the lecture. So mean center, given a set of points. Okay, be careful here. A set of points, and each point is addressed by x and y, which means each point can be found within space. And you can use this pair of coordinates to find it. So spatial context here has been added. The mean center, x bar, y bar, be careful here. X bar, x and y, no matter x, x1, y1, x2, y2, xn, yn, x bar, y bar, they are for coordinates. X is usually for horizontal coordinate, y is usually for vertical coordinate, right? The mean center is calculated as this. X bar equals to the mean of x. Y bar equals the mean of y. Okay, if you separate them, left side we have a formula for mean value. On the right side we have another, actually the same formula for mean value, is just y instead of x. You will say, where is the spatial context? X and y, they are addressing the space, because x and y, like I said, they are coordinates. So here, the mean of x has a spatial context, because when you find the mean value for x, you actually find a coordinate for x. Similarly, you will find a coordinate for y. These two coordinates, one is actually x bar, another one is y bar. And you use x bar and y bar to find a point within this space. And that point is the mean center of the set of points. Okay, so this is mean center. So the mean center could be inside the polygon you are trying to address, like this circle or ellipse, or this triangle, or could be outside of your polygon. Okay. Actually, this mean center has another name, is called centroid. It's the center of a polygon, and it is also the mass center of uniform density, which means that if you consider each polygon here has a specific mass, has a specific weight, and this weight or this mass is evenly distributed within this polygon, then the centroid or mean center can be considered as the mass center of that polygon. So this mass center or centroid or mean center could be inside, could be outside. When you find out X bar and Y bar, you will know that specific location for centroid, right? And then you will know it is outside, whether it is outside the polygon or inside the polygon. And the weighted mean center is something based on mean center. You simply add some weights into the calculation. Into the calculation. In some cases, weights can be put on every point to calculate weighted mean center. So you can say X bar, Y bar, they are still purposes, but for X bar, each term is not only Xi. You need to use Xi to multiplicate Wi, which is the weight for Xi. And then the denominator changed to, it's the sum of weights from all locations. Okay, you say, what do you mean weight? What can I, what can be considered as a weight? Population can be considered as a weight. Okay, okay. Weighted centroid, mass center of non-uniform density. Okay, here is an example. So this is a map for United States, and here we have small purple triangles. Each triangle is a mean center of population for US within a specific year. So for 1790, the mean center of United States, population mean center of United States is somewhere in Maryland, New England area. And then 1800 to the west a little bit, 1810 to the left, to the left, to the left. For year 2000, the mean center of US population is somewhere in Missouri. So you can say the mean center of the population is moving west in the last more than 200 years. Why? Because the population was marching to the west. First immigrants of this country arrived on the east coast of the United States, right? And they expanded their homeland to the west gradually in the last 200 years. That's the reason why the mean center of population of US is also moving west. So here, let's get back. How to calculate the mean center of population in US? You can consider Xi as the centroid of each state. Okay, so let me repeat this. Xi as the x coordinate of each state's centroid, or each state's geometric center. Y is the y coordinate of each state's centroid, geometric center, right? So for Ohio, for example, you can find out the centroid of Ohio. It must have, of course, a latitude and longitude, right? A longitude can be addressed by y. A latitude, for example, address it by x, or you can just reverse that. Doesn't matter. And wi can be used to address the population of that state. Okay, so for a specific state, for example, Ohio, you use the population of Ohio to multiply the x of the centroid of Ohio. Then you do this for 50 states. You use the population of that state to multiplicate the x value of that state's centroid. You do this for the numerator, of course. For the denominator, what's that? It's the total population of the US, right? Then after this calculation, you find the x value for the mean center of population in the United States. And you do this again to calculate y bar. And then you will find what? The mean center of population for United States. This is how the author of this map finished it. So of course, you need to find out each state's population for 1790, right? And then find out all the centroids for all states in that year, right? And you repeatedly do this for all those years, and you will find the mean center of population for United States. Okay, beyond that, we can also find out something called median center, the location that minimizes the sum of distances from all other points to that central location. That central location is the median center, and it is an iterative calculation. We use x prime and y prime, this pair of coordinates, to address the location of median center. Why is it an iterative calculation? Because there is no single or multiple formula can finish this calculation for mean center in one step. Actually, in order to find out median center, you have to find the mean center of the area or of the polygon first. And then you calculate the distance between mean center and several other or many other, as many as you want, many other locations. You find the distance between that mean center and multiple locations, and you try to minimize the sum of this distance. In this process, you will just adjust the position of the original mean center multiple times. That's the reason why this process is called iterative calculation. And eventually, usually we use computers to help us do this. You will find that location, x prime, y prime, which minimizes the sum of distances from itself to all other points you are interested in within the polygon. Okay, that's median center. And just like mean center and weighted mean center, we can still apply this idea of weights to mean center and add WI to the statistics and find out weighted median center. So WI is the weight for a specific location I. Here, there is a new parameter is called DI, is the distance from point I to the central location. Okay. So here, applying the idea of median center, you can still find multiple median centers of population for United States from 1880 to 2000. Again, it is still moving west and moving south. If you compare the vertical direction here, it makes sense, right? People march to the west to develop more lands, and today California, which is on the west coast of the United States, I believe it is state with the highest population of the country, right? So you can say that people are moving west. That's the reason why mean center and median center of population for US, they are both moving west in the last 2 centuries. Okay. Okay, then let's talk about variability with spatial context. The first idea, the first concept I want to introduce here is called standard distance. So the square root of the average square distance of points to the mean center. Mean center is the centroid of a polygon, right? And it is addressed by x bar and y bar. So for this standard distance, it's called SD. So D here is used to differentiate from standard deviation, which is simply S, right? So here N, again, N is just the number of observations, right? DIC is something new. DIC square or DIC square. DIC itself is actually the Euclidean distance between point I and the mean center of the polygon. If you square it, it's DIC square. On the right side, we do not have the square root anymore, but here you can say the distance between xi and x bar square plus distance between yi and y bar square. This is actually trying to calculate the Euclidean distance between xi, yi, and x bar, y bar, and x bar, y bar is the mean center, right? So yeah, very simple. Standard distance. You say, why is it called standard distance? Because you use this n here to standardize the, 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 the squared sum of Euclidean distances between all other points to between all other points and the mean center. Okay. Okay. Of course, if you do not like the square, you can just simply remove the square and remove the square root and remove the square above this DIC. Yeah, some people they use this simplified formula to define SD, but the idea here is the same. It's something standardized or normalized because there is denominator and yeah, you simply use the number of observation to do that, to carry out the normalization or standardization. Okay, and based on that, this is the last concept I want to introduce in this lecture. It's called relative distance. Okay, dividing the standard distance SD by the radius of a circle with area equal to the size of the study area. This sentence is long and complex, but let me tell you what it is trying to express. So you need to calculate SD first, standard distance first. Okay, that's for sure. And then you have a study area, right? You have a study polygon. After the calculation of SD, you need to figure out the size of the study area. And after that, no matter that area, that polygon is circle or not, you need to assume that it is a circle. And since you know the size of that assumed circle, you can calculate the radius of that circle, which means that no matter that study area is circle or not, you will consider it as a circle and use its size to calculate the radius of that circle, even though that circle might be just in your mind because the polygon is not a circle. Okay, so that's the tricky part. So standardized by the size of study area S. So relative distance is called SD REL, REL for relative. It is simple. It is the ratio between standard distance and that radius I just discussed, right? But how to calculate that radius? Of course, like I said, you need to know the size of the study area as here. A is the size of the study area. It is not standard deviation. Be careful with that. And of course, if you use pi to divide that area and you calculate the the square root of this ratio, you get R. It is simply from the formula of a circle size, pi multiply the square of R, S equals pi multiply the square of R. But now you know S, you know pi, how to calculate R. This is how you calculate R, right? So you need to calculate the standard distance first and then find out that R based on the size of your study area. So where S is the size of the study area, is not standard deviation. SD is the standard distance, R is the radius of the circle who has the same size as the study area. Okay, so this is the last statistic I want to introduce for this lecture. Okay, that's all about descriptive statistics you need to know for this class. And from our next lecture, we're going to introduce something new. And yeah, here you may have noticed, and in the previous lecture, I'm not sure, lecture 3 or lecture 2, I forgot to cover this part of the slide. Actually, I covered this GOG 5100 for most slides of this class, but I left this one. Now this class is GOG 4103, right? 5100 used to be the code of this class, okay? And now it is 4000 level, but it used to be 5000 level because there is another class as intermediate spatial data analysis existing in the department. And I'm not sure if it is using this specific old code for this class, but for now, this class is 4103, and its content is the same as before when it was GOG 5100. If you were feeling confused about this code to the bottom left of this slide, that's the reason why. So don't worry about that. Okay, this is GOG 4103. It's not GOG 5100. It was the code for this class 1 year ago. Okay, I will just stop here. I will see you in the next lecture.